Let's continue. Let's do one example. So far we looked at just the time complexity and how to look at how to use the formulas, the iterative approach to analyze iterative algorithms. Okay. Now we can use those formulas to also analyze space complexity, and one scenario is what we have seen in 228 in the list ADT. So if you remember, in the dynamic list ADT, then we implemented as an array. We followed this approach of doubling the array size. Okay, so we started with an array of size 1, max size is 1, and that is at base that is 100, and the array pointer points to the base that is 100, the starting arrays. So if I want to insert one more element to this list, I have to increase the array size. So we decided to double the array size. So this is now the new block of array. So this is one block of array, this is another block of array that we have to create, and then copy the values from the old block to the new block. So copy the 20 to 20 and then insert 45. So this is at some new address 200. Then if we have to further insert anything, there's no space in the current arrays or list, so we have to double the array, basically create a new block of memory whose size is twice the previous array size, and then copy all the values from the previous array to the new block of array, and then insert the values we want to insert, and then you again keep doubling and so on. So the number of memory cells that we allocate here is 1 memory cell, then 2 memory cells, that is 4, and it is 8. So it is going to be 1 plus 2 plus 4 plus 8, in this case if you stop up to 8 memory cells. So that means you are totally allocating 15 memory cells as you go through this process of resizing. Now in general, if you are given n elements, where n is say a perfect square of 2, by perfect square I means like 8 is something like that, because we can say 8 is 2 cube. 16 is also like that, because 16 is 2 to the power 4, and so on. So in general, if we have n like a square of 2, is going to be the number of memory cells we are allocating is 1 plus 2 plus 4 plus 8 all the way up to n. So in the earlier example it is up to 8, then you can go to 16, then 32, and so on. So what is this summation? That's what we want to solve. So 1 plus 2 plus 4 plus 8 plus n, as you can see, you have exponents of 2. So this is 2 raised to 0 plus 2 raised to 1 plus 2 cube plus 2 cube, and as I said, n is some square of 2, so we can say n is some 2 to the power k. So we have seen a formula for this. So if we have 2 raised to 0, 2 raised to 1, 2 cube up to some 2 raised to say n minus 1, and here it is 2 raised to k. We can say it is 2 raised to k plus 1 minus 1 divided by 2 minus 1. That's the formula. If you go back and look at the formulas you have seen here, if it is 2 raised a and it's up to n, a raised to n plus 1 minus 1 divided by a minus 1. So here it is I equals 0 to k, 2 raised to I. That's what we had, 2 raised to 0 plus 2 raised to 1 plus 2 square up to 2 raised to k. That's going to be 2 raised to k plus 1 minus 1 divided by 2 minus 1. And this is for a not equal to 1, and in our case a is 2. So that's the formula I have applied here. So it's going to be 2 raised to k plus 1 minus 1 divided by 2 minus 1. So the denominator is 2 minus 1, that's just 1. So you don't need to write the denominator. Now the numerator, you have 2 raised to k plus 1, and that can be written as 2 times 2 raised to k. Now what is 2 raised to k? 2 raised to k is n. So we can simply say the final result is 2n minus 1. So in the case of 15, n is 8. Right, so 15 can be written as 2 times n 8 minus 1. 2 times 8 is 16, minus 1 is 15. If n is 16, then 1 plus 2 plus 4 plus 8 plus 16 is going to be 2 times 16 minus 1, which is 31, and so on. So 2n minus 1 is state of n. Okay, so that's the number of memory cells we are allocating, because we can discard the lower order terms and discard the coefficient of the most dominating term, and we are simply left with n. So that's the theta time complexity. And this is a tight bond because we have to always create proportional to n. Okay. Now this is doubling the array size is what the strategy we used, but we discussed in the data structures class another approach that one could commonly think of. When you want to increase the array size, why can't you just increment the array size by 1? So if you have an array of size 1 and it is filled up, you create a block of memory whose size is 1 more than the previous array, and if that also gets filled up, create another block of memory whose size is 1 more than the previous block of memory, and so on. So the number of memory cells that we end up allocating, if you want to really create only up to 4 integers and store in the list, is going to be 1 plus 2 plus 3 plus 4. So 1, 2, 3, 4. So that is like 10 memory cells. And if you want to do it for 8 elements, it is 1 plus 2 plus 3 up to 8. And we can use the n times n plus 1 over 2 formula. So that's going to be 36. So in general, if you have to store n elements, and you are starting from a list of size 1 and you are incrementing the list size by 1 each time, the number of memory cells will be allocated is 1 plus 2 plus 3 up to n. That's going to be n times n plus 1 over 2, which is that of n square. So what we find out is, if you increment the array size by 1, you end up spending that of n square space rather than that of n space by doubling the array size. And not only that, when you look at from the point of view of time complexity, because when you kind of double the array size or even increment the size by 1 and basically create a new block of memory, you have to copy the values from the previous block of memory to the new block of memory. So for this resizing operation, the copy operation is the basic operation. Or for the resizing method, the copy operation is the basic operation that has to be done repeatedly. So in the case of doubling the array size, you can consider this 2n minus 1 as the number of times we do the copy operation, because we have to really copy from the old block to the new block and so on. On the other hand, the incrementing the array size by 1, the time complexity of the copy operation is also going to correspond to the number of memory cells you are going to create. So one copy operation from this array to this array, then 2 copy operations from this array to this array, then 3 copy operations from this array to this array, and so on. So in addition to considering this for space, we can also do a similar analysis and come up with the time complexity for of this approach, okay, of resizing. Right, we stop with this and save this video. Any question?